Hello friends, how are you all today? Have you ever wondered what operating system is and how it is going to work? It's coming up right now. I'm Prashant, a technical trainer and freelancer from Dharani Academy of Technical Education, Bengaluru. Let's start with the concepts of operating systems. We were discussing about the calculation of the effective access time, right? And we solved one problem on the same concept. Okay, so the next topic is called as copy on write. Okay, so in the previous section we saw how a process can start very quickly, right? Whenever the demand paging in which the page containing the first instruction, right? So we saw that if the first instruction says that there is no the contents are not present in a page, right? We know that demand paging is the basic idea to do that. All right. There is another option. That option is called as using a function called fork, right? So it's a system call. Initially you can bypass the I'll repeat. uh, when we say that we can create the process by using a system call, right? So that's our idea here. A process creation, we can create a process using what is called as a function, that is fork, right? This particular function is called a system call. Okay, if you have come across what are the system calls, system calls are the functions that OS is going to call whenever it has to perform a most simple or most basic operation. Okay, so for example, you can see here this particular fork system call is used for creation of a process. Okay, in this case, right, demand paging can be bypassed using a technique, right, which is very similar to the page sharing technique. Okay, there is one concept called as page sharing, right, in which you have a specific value and you can actually share that particular page, right? So let's try to write that point now. We'll discuss about this in detail later. Okay. uh, this system call may bypass, you may skip, right, the need for what is called as a demand paging. This can be done because function has all the resources that are needed to create the process. So because of that reason, you don't have to go for a demand paging. Okay, by using what is called as a page sharing. Okay, you share the page, right, using which you can actually perform the you can actually call the system function system call, which is called as a fork, and you can create the process. All right, now what is the advantage of this technique, right? This technique, it provides, when we call this, it provides a rapid, it provides a rapid process creation technique. It creates a process very quickly, and also minimizes minimizes the number of new pages. Okay, the number of new pages that must be allowed to the newly created process. So when we create a process may require several number of pages to be created for its usage. So what we are going to look now is that we try to minimize the number of new pages that must be allocated, to the newly created process. All right, so this can be minimized. All right, so we'll see how this is going to work now. So before that, let's look at the fork system call. All right, so fork, right? It's the common name given by all the operating systems to a specific system call that creates a child process. Okay, so fork is a system call that creates a child process, right? So what is a child process? When a process is generating another process, so the newly generated process is called as a child process, and the one which creates the child process is called as a parent process. Okay, so it's called as a parent uh, process. So now fork will be the parent, and it is going to generate a child process. So we want to generate a process means we have to call this particular system call. Okay, so system call that creates a child process as a duplicate. It's a duplicate of its parent. So normally this fork worked by creating a copy of the parent's address space for the child, duplicating the pages that belongs to the parent. In the sense, see, when I say that I'm creating a new process which is very similar to the parent, what are the things you need to copy? Right? You need to copy, right, the address space. So this implies I just write what you are trying to do here, right? So you are trying to make a copy of the address space of parent must be present because I'm copying whatever that already exists. Okay, so that's first thing. And also you are trying to duplicate the pages belonging to the parent. Okay, so you duplicate the pages belonging to the parent. This is what we are going to do. Okay. Okay, now let us consider that there are many child processes which try to invoke another system call which is execute, exec. There is another function called as exec. Okay, so I'll write that exec. right? In this case, you see that right, we are trying to execute the child processes immediately after the creation of the process. So this is a system call execute process. Any process which has to be executed, you need to call a system call by the name which is exec. Okay, when you call this, it means it will execute the particular function. Now you see that, let's assume a case where we have created multiple child processes, and multiple child processes, uh, they are calling the execute system call immediately after the creation. Okay, so in such case, what we try to do here is that we use a technique called copy on write, which works by allowing the parent and the child processes initially to share the same pages, right? Because as soon as a process gets created, there may not be the parent's address space completely available with the child process. Okay, so when you say that there is a parent process, it has its address, it has its own pages, but all the pages might not be copied to a child process. Okay, so in such case, what we do here is we use a technique called copy on write, right? That's what was the slide heading we wrote, okay, which allows us to share the same pages with the parent and the child. So how we'll do that, we'll see now. Okay, so let's write another point here about this exec function. Why we wrote this exec, execute system call? Because uh, let let us assume, okay, uh, let many child processes invoke, or they call, okay, invoke this particular exec function, right? Exec immediately after creation, after the creation. So this means as soon as they are created, you are calling, you are making them to execute it. It means there may not be right, there may not be the pages which have been copied to the child process does not have the sufficiently required number of pages that are actually present in the parent. Okay, it's not there, but still you are making it to what you call, you are trying to run that particular code. Okay, right, so we'll write here after creation, comma, without, we'll write the condition, without having the copy of the parent address space or the pages. You don't have it, but you still try to run it, right? What you can do, right, in such case, we use a technique called copy on write. So in such cases, the copy on write, this particular copy on write technique can be used, which allows the parent and the child processes the parent and child processes initially to share, right? What we want to share the same pages, because pages are not available with the child processes, right? So these shared pages are marked as something like copy on write page, meaning that if either of the process writes to a shared page, a copy of the shared page is created. Okay, so we'll see that the meaning later, how that will be done. But how this is going to work, we said that okay, they share the same pages. Now these shared pages, these shared pages, let's say they are marked as, they are marked as copy on write. See, the name says that copy on write, in the sense you are making a copy. Okay, copy on write pages. Whichever pages are shared between the parent and the child, you are going to call it as, right, copy on write pages. So what is the meaning? We'll write. So meaning that, so either uh, process, if okay, we can say either process if writes to a shared page, right? Parent or the child, if it tries to write a such a shared page, right, you immediately make a copy of that page. Okay, so a copy of the shared page is created. Okay, all right, so let's look at the idea, right, how this is going to be created. You're using a diagrams. All right, so first, okay, let's write a diagram where, so there are say three different pages, and one of the process is trying to alter a specific page. Okay, so let's try to make a diagram. So this is process, say process one, and I'll write another process over here. Okay, before that, let's make the physical memory. So this is the physical memory which is available, and copy another page. Okay, so let's assume that this is the second process, process number two. So I'll just write the names. This is, say, first process. Can be parent or child. Okay, doesn't matter. This is process number two, and this central shape represents the physical. So in which let us consider some regions of codes, and each region of code is trying to alter a specific page in the physical memory. Let's assume that. Okay, so these are the several pages. So say this is uh, page A, this is page B, this is page C. Okay, now let us say the first part is actually referring to page A, second part is referring to this, and third part is referring to C. And similarly, in the different process, that is process 2, we have three different sections of codes. Again, they are actually accessing the similar pages, page A, page B, and page C. Okay, so this diagram is a original diagram. Let's consider that it's a original case, so we can call it like before. uh, in which in the next diagram we are going to see that the one of these two processes, like process 1 or process 2, tries to modify a specific page before any process. In a sense, process 1 or process 2 modifies, okay, any process, before any process modifies uh, any pages. Okay, it's not yet modified, right? So we are considering this to be the initial condition. Okay, now the second diagram, we are trying to write whenever somebody is trying to make a copy, what happens. Okay, that will be our next diagram. All right, so let's try to make a diagram now. So that is, so the same, this is process number 1, and I have another process, that is process number 2. Okay, so this is the process number 2, and at the center we have the physical memory. All right, process 1, process 2, this is PM, indicating physical memory. So now we'll denote the same three pages. So this is page A. Okay, then you had another page, that is page B, and you had a page C. Okay, now the copy on right says that if at all any of the process tries to change a particular page, you need to make a copy of that page. In the sense, this is accessing this is actually accessing this. But now my third part of the code in process 1 is modifying page C. In the sense, page C will be as it is, but whenever it modifies, there will be a new copy. So that is, copy of the page C will be created, and you are actually modifying that, so that, right, your original page is intact. This is not going to be changed because my code is actually accessing this. The process 2 will be accessing that. Okay, so because of that reason, now this will not alter, right, what exactly has been uh, created at the original place. So right, so copy of this we marked now. But with respect to the process 2, right, the three sets of codes which were actually trying to access the three different regions of the physical memory, they are still there as it is, no change. Okay, they are connected to that. Okay, it tries to, the third part of the code tries to access page C, second one access page B, one access page A. So the basic idea here is that right? Whenever process 1 modifies a particular page C, right? We saw what was the case. It was the first diagram. Now, once it modifies, contents of the physical memory, right? Uh, we can see there is a change. Copy of C will be created. Okay, so there are two cases here to understand the whole process. So we discuss each one now. So let us assume that the child process attempts to modify a page containing maybe general memory, or it can be a stack. Okay, so with pages set to be copy on write, let's say that there is a stack memory. You can consider any part of the memory, that's fine. Okay, because any part of the memory, the same concept will be applied there. Okay, now let us assume that, because textbook says that they are considering stack for this explanation purpose, so we'll consider the same. All right. Okay, so assume that the child process attempts to modify a page, right? So let the child process attempts to modify a page that contains, so I can say containing uh, portions of the stack, right? Again, let us make it more clear. That region of the stack has the pages set to copy on write. In the sense, it's shared between the child process and its parent process. Okay, so that is indicated by saying with the pages set to again, right, set to be copy on write. This is the condition. So now what happens? The operating system will create a copy of this page, mapping it to the address space of the child process. Whoever, right, whichever child process is trying to make an attempt to modify that page, right? OS will create a copy of that page, map, and it maps the address to the child process, right? That's what is the copy on write. So next point will write, then the operating system OS will do what? Will create a copy of this page. Will create a copy of this page, and it performs a mapping it to mapping it to the address space of the child process. So the child process will then modify the copied page, right? And it will not change anything that is actually related to the parent's process, right? Because now you are actually making a copy, right? So when the copy on write technique is used, only the pages that are modified by either of the process are copied. Unmodified pages can be shared by the parent and the child process. So that's the whole idea here. So ultimately we can see that the child process will modify the copy of the original thing. It will not touch the original or the parent process's page. So this indicates that uh, I can write, therefore uh, when the copy on right, this particular technique is used, whenever this is used, uh, we can say that only only the pages that are modified, we can say that modified by either of the process. The same thing, just now we discussed only about the child process, but it holds good with the parent process as well. That's why we don't discuss the second half, we simply write the statement. Okay, so pages that are modified by either process, either process are copied and all unmodified pages can be shared by the parent and the child process, right? Both processes can share the unaltered pages, right? Whichever is not modified, you can still they can be shared. Okay, but whatever is modified will be present with the one who is modifying that particular page. It's the copy of the original thing. All right, so now let's look at the operating system's process. When OS comes to know that a page is going to be duplicated by using this particular technique, right? It is important to note the location from which free page it will be allocated, because there will be a lot of pages kept free for this purpose. All right, all the OS will keep certain number of pages, right, that can be shared and that can be modified. We call it as a free page. So each OS will have certain free pages which can be used for the sharing, as well as what you call the copy on write that can be performed on such pages, right? So what has to be done now? I have so many pages with available. Now I need to identify, right, which particular free page is going to be used, or which free page will be allocated for that particular process, so that it can modify or copy the content of some other page. Okay, so for that reason, what happens, many operating systems like Windows, Linux, Solaris, anything you consider, every uh, OS will provide a pool of free pages, so that, right, it can allocate that particular page, right, so that it can be applied to a duplicating process. All right, so now the idea is that the operating system contains free pages that can be allocated to the processes which want to duplicate the contents of some other pages. Okay, whichever process wants to copy the contents of some other pages, right, they can be using, right, the free pages. Okay, so such what you call the free pages are actually called as pools. Okay, uh, create a pool from where any process can take the free pages. Whenever there is a demand, you can actually allocate any number of pages. Now, OS typically allocate these pages using a technique that is called as zero fill on demand, right? So the technique that allocates free pages from the pool to a process, right? Any process asking for memory, right? For performing this operation, right? That technique is called as zero fill on demand. Okay, let's write that point now. Every OS typically, we can say allocate, OS allocates these free pages, these free pages uh, to a process by using a technique called uh, zero fill on demand. So zero fill on demand is the name, right? So zero fill on demand pages have been zeroed out before being allocated. So, right, what do you mean by zero fill? Zero fill means you erase the previous contents. Whenever, that's why it's a free page. Okay, so these pages have been zeroed out before allocated, before you are allocating. So the pages will be uh, zeroed, Z-E-R-O-E-D, yeah, zeroed out. You zeroed out, zero it out before being created. So that means erase the previous contents. You simply erase the previous contents. Okay, so this whole concept of allocating, right, the free pages to the process which wants to share the memory with its parent process, right, is what is called as zero fill on demand. Okay, that's the technique. Then let us go ahead to the next topic, that is called as page replacement. Now, uh, so far we discussed that let us there is what is meant by page fault and how do you measure that by using a page fault rate, and right, we understood that, right, page fault may be occurring with some probability. Okay, so that idea was strictly speaking it may not be very accurate. That just gives an idea that okay, this could be the time, estimated time that is required to when a fault occurs. Okay, but in a strict sense, let's consider that a process of 10 pages actually uses maybe only 5 out of 10. Now you see that the demand paging will save the required loading of the 5 extra pages that is never used, right? So there are 10 pages of a process, right? But only 5 are required to be loaded so that the process can run at a given point of time. It means if you are using the idea of demand paging, virtual memory concept, right? You save the time required to read the other 5 pages which are not required. Okay, so we also understood that, right, we can increase the multi-programming concept here, because within the same space you can now run some other process, right, which uses the remaining five pages of the main memory. Okay, so when you have multiple frames, right, you can write only say if five pages are allocated. When you have 40, let's assume 40 frames I have in my memory. I have 40 different spaces available. If each process takes only five particular pages to run, right, then you can run eight processes. But if you don't do so, 10 each process is of size 10. 10 into 4 is 40. I can run only 4 process if you load everything. So loading everything and not loading everything will is the basic difference. This is what we understood so far. Now we are trying to increase the way in which you can actually run the multiple programs. Multi-programming concepts are supported when you go for virtual memory. This is what we understood so far. Okay, so all we are trying to increase the degree of multi-programming, right? Degree of multi-programming refers to I am trying to run multiple programs on the system, right? What we are actually performing is, we call it as over allocating the memory, right? In the sense, actually, right, for one process there will be only maybe 5 pages, but you see that the CPU utilization is higher and you need more memory for the execution of the what you call the process. So what we try to do here is that uh, okay, let's consider a situation so that this thing becomes very clear. Okay, what do you mean by over allocation of the memory, right? Okay, let's go with the requirement of page replacement. Why do you need a page replacement is what we need to look at that. Okay, so that means so far what we understood, whenever we are trying to go for a virtual memory, right, it saves the total space required by one particular process. You allocate only the pages which are required. The pages which are not required, you are not loading. Okay, that means, right, you are going to run multiple programs in the same memory. This is very clear. So I'll write that point once again now. uh, when you try to run multiple programs on the same memory by saving the memory, we call it as a multi-programming. If you try to run multiple programs at the same time, right, we call it as a multi-programming environment. When you try to increase the number of programs in that environment, we call it as increasing the degree of multi-programming. So let's write that. We'll directly start from there. So if we try to increase the degree of multi-programming, right, what you are trying to do here, this implies uh, we are actually over allocating the memory. In the sense, the same memory is being allocated to many more users, many users than the fixed number of users. Okay, so right, we understood. So each process is taking 10 pages, but you allocate only 5 because at a given point of time only 5 are sufficient. So if at all there were 10 pages, I can load only 4 such process. 10 plus 10 plus 10 plus 10, 40. I have 40. I'm assuming I have 40 pages. So you can load only 4. But if 5 pages are allocated for each process, you can actually run 8 such processes. You see, you are increasing the number of programs that can run. So that's what is multi-programming. When you increase this, you see that you are over allocating the memory, right? So the number of frames that can be executed is just 5. You reduce this, the number, from 10 to 5, so that your total number of uh, processes that you can run is increased. Okay, fine. So that's what is the meaning of over allocating this memory. Now, over allocation of memory means, while one user process is executing, right, let us assume that there is a page fault occurring. So the OS, what happens with the OS will determine where the desired page is residing on the disk. Okay, but then it finds that there are no free frames available on the free frame list. Okay, because let's say all the memory is in use, every memory that is present as a free, because you see that there are instead of you run only one code or two code or codes of two or three processes, now you are running 8 processes, right? So the all the free frame whatever we discussed in the previous topic, let us say now it is not available because multiple things are running, and there may be a situation where no free frame is available. Okay, let's see that. If that happens, what's going to happen and how we are going to handle that, right? The solution comes as a page replacement. All right, okay, so we'll write the problem now. So we are still discussing about what is the problem and why do you need the page replacement. Okay, we are over allocating the memory, indicating that there are multiple processes running. That's what we have written now. So let's say while a user process is executing and page fault occurs. If at all a page occurs, then the operating system first determines what it determines. It will determine where the page is residing on the disk. Okay, determines where the page is residing on the disk. This is what we saw in yesterday's discussion, right? Where, right, you are going to find a copy of the original content whichever is missing. Okay, it finds out that okay, the copy of this is present at this location of the disk, but now you have a problem. But because there are multiple uh, processes are running at a given point of time, now because of the multi-programming environment, we find that no free frames are available on the free frame list and all are in use. This is an assumption, this is the worst case. Okay, normally one or two free frames may be available so that you can use it. If it is available, you can use, but now we are trying to consider what happens in the worst case. So we extend this sentence saying that what we can say, but finds that, since OS finds that there are no free frames, no free frames on the free frame list. This means what? Complete memory, right? All memory uh, is in use, it's being used. Okay, so let's try to write a simple diagram to understand what happens here and why the replacement is required. Okay, let's consider, say, logical memory for different users and a page table and corresponding to a physical memory. We'll write these things. Okay, so let's say this is the logical memory for, say, first user. When I have a logical memory corresponding to logical memory, I'm expecting a page table. Okay, this is logical memory. So I'll write U1 indicating that this is user 1. Okay, then I'll write the page table of user 1. Okay, user 1 is a particular process, right? Very similar to this, let's now write another logical memory. This is for user 2 and corresponding to that user, the second process, we have to write what is called as the page table. Okay, so this is, again, this is LM, logical memory of, this is user 2, and this is, I'll just write PT, page table of user 2. All right, now let us say the logical memory has say 4 different locations, 1, 2, 3, 4, and let's say user 2 also uses 4 different locations. Okay, so we know that the address will be starting from 0, 1, 3, and let us say right now the program counter is pointing here, so this is PC, right? And we also know that the page table requires something like this. So the frame values, we know that there will be frames like this, 3, 4, 5, and this is valid, 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 and this is invalid. Okay, now let's write the same thing corresponding to the user 2. Okay, say this is 0, 1, 2, and 3, and let's say this is A, B, C, D, something else. Okay, so here I'll write say H, then I write load M, and then J, then okay, let's say this is what we have. Now let's write the physical memory, because physical memory is sorry, before the physical memory I'll finish the page table of second user. So this is the page table of the second user, and I have same 4 locations over here. Okay, say this is 6, valid, that is invalid, this is 2, valid, this is 7, valid. Let's see. Okay, now let's go to okay, physical memory. Let's write the physical memory. Okay, so this is the physical memory. Right. Okay, now let's say this has 4. Okay, let's create 8. Let's consider 8 locations. So physical memory, this is physical memory. So we have physical address coming up 0, 1, 2, 5, 6, 7. Right, so you can see that the 3, 4, 5 are actually the locations of H, load M, and uh, J. Okay, okay, let's write 3, 4, and 5 is valid. So let's write this. So 2 should be, let's say this is D, then 3 should be, let's say H, then this should be load M. So this is say J, this is A, this is E. Okay. All right. Now it understands that uh, a particular process is executing and a page fault will occur, right? Because when I say a particular uh, I'm trying to access a particular function and that particular function is not available, right? Because you say you are saying that load M. So why the page fault occurs here? It's because you are pointing to the PC here. It says load M is your particular function, right? But I don't see the M which is located here at all, right? I don't see M. M is not it is right. Uh, it's an error, correct? Page fault. Right. So, but I don't have any space left over in the whole right, memory, right? Because I can assume that I have something else present in the physical memory. So let me mark that. You have a maybe this is the swap area, or you can have some monitors monitoring this section. Okay, I'll write a monitor here because textbook says that you have a monitor here. There is a monitor here till this, in the sense some other process is using that locations, right? So 0 and 1 are not available. Okay, so under such condition, now you see that you have no space left. So we understood that if this is the case, right? Just now we wrote a point. The point said that whenever the page fault occurs and you have no space left over, right, in the physical memory, right, everything is filled, which means what you are going to do, right? I don't have any other option, right? But I need to perform what is called as a page replacement, right? Normally OS will have several options, right? It can terminate some of the processes, right? But normally that will not do that, right? So terminating the process is not a solution here, not an ideal solution, right? So we'll write the requirement now. So under such situations, right? What is a such situation, right? No free frames are present. That's what we have written so far. Just let's go back and check, right? All the memory is in use. There is no free frame, right? Which means what? Under we showed we showed such a situation in this diagram. You can simply write this diagram, which makes sure that there is no free frame left over, right? Which means, right, under such situation, right, the OS performs what is called as page replacement. One important question that normally appears is that what is the requirement? Elaborate the requirement of page replacement. So in such case, our answer should be starting from the top, saying that multiple processes trying to access this page, and we say that, right, there is no free frame left over. So write this diagram and then justify saying that, okay, under such condition, we don't have any other option, but we have to perform what is called as a page replacement.
That's all for the day. Let's resume the concepts in the upcoming classes. If you have any doubts related to the topics we discussed, please feel free to contact me anytime. Thanks for watching. Have a nice day. Goodbye.